Yeah, people have found it hard, but really, there's not. We can do it. It's just again, just like when we did the greedy algorithm. I'm going to give you a set of steps. You do these steps. You plug in what you need to along the way, and hopefully you understand it. And hopefully that when you go out in the real world, you can write dynamic programming algorithms. Now, I certainly know if you ever do the ACM contest, at least one or two of the problems will be dynamic programming algorithms. But I can also pretty much assure you that if you work for a bank, doing, moving money around and stuff, you will never write a dynamic programming algorithm. So I'm not absolutely claiming it's the most useful thing you're ever going to do in your life, but it's a good thing to do. In some ways, recursive backtracking, which isn't actually listed on the course syllabus, I think in some ways is even more important, because it's an algorithm which you can do to solve anything, but it might run in exponential time. Right? So...
Is that true? It can solve anything? It just might take forever?
No. As soon as I said anything, I have this thing about anything. Because any generalization is false. But what I meant by anything is I meant any NP-complete problem. You certainly can't solve the halting problem because it's undecidable. All right, so this is exactly what I just said, right? There's one of the things I didn't like about the Corman book, you've probably seen it, it's this big book on algorithms, and everybody in computer science should own it because it gives you the code for lots and lots of algorithms. But one of the things I didn't like about it is that every time it presented an algorithm, it presented a nice optimized piece of code. And then it would be harder for you to see what's unified about all these things. And so when we do dynamic programming, we're going to make them all look the same, right? We're going to try to make one picture. This is what a dynamic programming algorithm is going to look like, and you all make it look like this, and that way there's less chance that it'll be wrong, right? And again, this is just what I said. We have a set of steps and analogies, and you learn them, and you fill in the details for the given problem that you care about. All right. So, if you ask about optimization problems, my input's this, and I'm looking for an optimal solution. Generally, they're NP-complete, right? And if they're, what NP-complete means, if you learn nothing else about the word NP-complete, you should know it means we have no polytime algorithm for it, meaning the fastest algorithm for it takes exponential time, which means if you have a reasonable size input, you won't finish it in your lifetime, right? But for those that do have fast algorithms, they tend to be dynamic programming. Right? So for the problems that are NP-complete, often industry wants to be able to solve them and can't have a general purpose algorithm because we don't know one. But there are heuristics, and what is a heuristic is you try different things and you just hope that you get the right answer. And in terms of optimization, you hope that you get a feasible solution that's reasonably close to optimal. Right? You don't have a guarantee that you'll get optimal, but maybe you'll get somewhere close. Right? And so when we look at recursive backtracking, it'll be ways of thinking about heuristics and thinking about ways of designing algorithms. All right? So we're going to start with, okay, this is just a review of what an optimization problem is. You're given an input. Now, when we were talking about dynamic programming, when we were talking about greedy algorithms, the input was a set of objects and you had to make a decision about each. And that's fairly general, but maybe we have, the input could be a graph, but of course you could think of a graph as a set of edges, right? So, and then a solution is every input instance has this exponential set of solutions, and given a solution, particular solution, it's easy to check, hey, is this a valid solution, and if so, what's its cost? And the goal given an instance is to find a solution with optimal cost. Everybody remember all this? All right. The solution might not be unique, and this is just. All right, so we're going to start with doing ST, finding the shortest path from S to T again. We've done that before, and you know, the easy algorithm is Dijkstra, so you don't have to be doing fancy things we're doing here. But I like this as an example because graphs are very graphical. You can see them, you can think about them kind of clearly, and it'll give us a nice clean place to start. And really, as I say, every dynamic programming algorithm can be thought of as finding a path from S to T, you know, doing the same, following these same steps. All right, so the input is a graph with node S and T, and the graph has directed weights, edges with weights on them, and I'm going to require this extra requirement that the graph is layered. And what does that mean? It just means we can draw it on the board so that every edge goes down, right? You don't have edges coming back up. Right? Everybody kind of get that? One thing that gives us for free is that there are no cycles, right? It's a DAG. And we have a source and a sink, and our goal is to find the shortest path from S to T. So again, a solution is a path from S to T, right? So if a solution is a subset of the edges, and it's a valid solution if it connects S and T, and we're looking, and then the cost of a solution is of course the sum of the edges, and our goal is to find the one with the minimum cost, right? So again, just like when I kept stressing when we were doing greedy algorithms and everything else, really, when you read a question on the test, the first thing to make sure is you understand what the problem is. Right? What are the solutions? What are the instances? What are the solutions? How do you know it's valid? What's the cost of a solution? Try to minimize it or maximize it. Right? All right, so before you start writing, pause and think about that. All right, what's the brute force algorithm? Is you try every path from S to T. How many paths are there from S to T? Is it a polynomial number? There's an exponential number. Here's, if you want a little simple example, right? You could go this way or this way or this way or this way, right? So the number of paths in this little example is 2 to the number of choices there, right? So with all of it, just like in the greedy algorithm, you know, we made a decision about each object. What we have here is we have to make a sequence of decisions, right? So we're gonna ask a question about the solution, and later I'm gonna talk about little birds. You know, before we had a fairy godmother, now we have a little bird. So she has a solution. We're gonna ask her a question. Think about you standing here. What's the obvious first question to ask about the solution? Where do I go? Right? Where do I go from here? Right? Tell me the first edge. Right? So the first obvious question is, which edge should I take first? Right? And somehow you have to decide which edge to take first. And when we did the greedy algorithm, how did we decide which edge to take first? Somehow we had some greedy criteria. We took the one with the smallest value, the best one. Exactly. So, and then if we were doing greedy, we would keep taking the best. But now, instead, we're going to recurse. Right? We're going to ask, somehow we decide this edge, and now we want to ask my friend a question. What's the obvious question to ask a friend? Where to go next? No. No, not where to go next. That's what you ask birds. You ask birds where to go next. Friends, what do we do with, these are recursive friends. So what are we allowed to give a recursive friend?
Smaller instance of yourself.
Right. any instance as long as it meets the precondition and as long as it's smaller, right? And what does the friend give us? The friend gives us the solution meeting the postcondition, right? So what are we allowed to give the friend? We're allowed to give the friend a graph that's layered with weighted edges and some node S and some node T, right? And what will our friend give us in return? Will give us the shortest path from S to T, right? From his S to his T. So here, what's the obvious? I'm now, I was standing here. Somehow I got inspired by the gods. I moved down here. And now, what's the obvious thing to ask the friend?
Find the shortest path from there to T?
Exactly. We don't ask the next edge because that would kind of be micromanaging our friend, right? We ask, okay, friend, how do you get from V3 to T, right? And our friend is going to give us the optimal path, which is this. And now, being recursive, I have to take my friend's solution and I have to come up with a solution for my problem. Remember, my problem is the shortest path from S to T. And what's the clear answer I should come up with?
Add your edge to his.
Exactly. I take his path, I add my edge on it, and I say that's my answer.
So the other paths, you're not going to ask the other B's to do the same thing? You're only going to ask
This is only the first slide. We're going to be doing this for a couple days. All right? Remember, we just magically decided to go down this edge. We have to think about how we're going to do that. Right? All right. As you said, you could ask about the second edge, and somehow he decides, and his friend has asked the question, how do you take the third edge, right, and so forth. Oh, I guess I didn't quite get to recursion here. Again, if it was a greedy algorithm, we would be taking the best edge, but in this case, is the best edge, is that going to give you the right answer? No, right? And so this is the problem. In general, we have a problem of local decisions. It's easy to see what's locally the best thing to do, but it's hard to see what the long-term consequences are. So local decisions are easy. Example, what's the cheapest edge? Hard to see what the best path overall is going to be, right? And so sometimes if you make a local initial sacrifice, I take this first bad edge, then the long-term consequences are better, right? It's just like, do I study for the test on Monday or do I go out and party? Which one's, short-term sacrifice or long-term gain? All right? So now, we have this problem of which edge to take next and how we should decide. And the truth is, we have no way of deciding, and what we're going to do, as you might have implied, is we're going to try them all. All right? But I find it's useful to tell stories and to think about things in a different way. And so, as I said, we're going to sort of ignore this fact that we try all edges and how we decide the first edge. And we're going to think about it by pretending that we have a little bird, and you can ask the little bird little questions. And so the little question is, I'm standing here at S. I ask, which edge do I take first? All right? So the bird is like non-determinism, and you learned in 2001 something about non-determinism, right? And right? So this higher power, this non-determinism gave you lots of information, but here you only can ask the little bird a little question. And we'll talk more about what that means to ask a little question. So, I'm assuming that she has a solution, a best path, and I ask her what edge to take first. She says, take this edge first, right? And then I ask my friend a question, and we could ask him what edge to take next, and he could have his bird and so forth, but as I said, that's micromanaging, right? So, we want to recurse. And remember, when we recurse, you can ask any problem, that instance that's smaller, that meets the precondition. We give him a sub-instance. So the bird says to take that edge, and we ask, and we walk along it. Now, the reason I like the bird is because when she says, take this edge, you want to think about trusting her, right? We trust her that she says that this is the best edge. At least temporarily we trust her. And so we walk along here and we stand here. And then we think, okay, given that the bird has told us that this is the best edge, now what's the rest of the problem? How do we think about a subinstance that we give to our friend? And the subinstance in this case is pretty straightforward. We ask the friend for the best path from B1 to T. Right? And whatever the friend gives us, then we get our solution by tacking the bird's edge back on. So this is going to be, in general, what happens is the bird gives you some information, the friend gives you the rest of the information. You tack the two together to get your solution. Right? Now, we also need to compute the cost of this solution. Well, the friend, we could easily, when you have a particular solution, you could compute the cost by just going through and adding up the edges. But we want to make our life a little easier. And in this case, the friend gives us the cost of his path, right? And we know the cost of this edge. So what's the cost of our path? So we add the two together, right? We didn't have to compute the whole thing. We just add this one number on. All right, everybody get what we're doing so far? Now, the truth is, we all know that we don't have a bird, right? So, just like when we were doing non-determinism in 2001, it was easier to design non-deterministic finite automata. And when you're doing the creative work, you just find this non-deterministic finite automata. And then there's a mechanical way of compiling it into this bigger deterministic finite automata. And that's kind of what we're doing here. If you have a faulty bird, then this might not be the optimal solution. Right? But the good news is that we haven't wasted our time. Right? We have learned something in this process. Any idea what we've learned? Well, we don't actually even know yet whether this is optimal. Right? So we don't know not to go there, but you're kind of right. What I like to think, this is an expression I think it's all good to memorize, is what we've learned. Right? What we've learned is, we've learned the best solution to our instance. Right? What this is a solution it's a valid solution to our instance, and it's best in some way. Right? The way it's best is it's best amongst those solutions to our problem that are consistent with this bird answer. Right? Of all the solutions to my problem that go through this edge, we now have the best one. Right? Does that make sense? So that's the best path from S to T that goes through that edge. And so what we're going to do is we're going to try them all. Right? So first we get the best path starting with that, and then we learn, again we come down here and we ask the friend how to get from here to here, the friend tells us this, we tack the two together, and what we now have is the best path from S to T of those that go through this edge. Right? And then we try the next one, we come down here, we trust the bird, we ask the friend how to get from here to here, he tells us, we tack them together, now we have the best path from S to T that goes through this edge, and then we do again through this edge. Right? Now what we have is we have four paths. Right? We have the best one that goes through this edge, the best that goes through this, the best of this, and the best of this. And for each we know their costs. Right? So now how do we find the best overall path?
Just find the one with the minimum.
We take the best of those. Right? We just take the best of the best. Alright? So we know all of these four paths, and we simply take the best of the best. And we know that that's the best overall path.
So how is this different than the recursion we learned before?
Well, in some ways it's not. It's an example of what we did before. The little difference is that you're trying these things and taking the best of the best. Right? We try different things, and for each thing that you try, you get a solution, and then you take the best of those.
How is this different than brute force?
Good question. It's not. It's not. Yeah, and we're going to get to that in a couple slides. In fact, it might be very shortly. But you're right. We're going to see that this is brute force. All right. So just I drew this picture a million years ago, and it's in the book. I don't know if it's useful or not, but we have one instance, and here's the set of all possible solutions to the instance. Right? There's an exponential number of them. And you can think about organizing these solutions into this game of 20 questions. You know the game of 20 questions? You have a question, I say, is it an animal or yes or no, right? And we branch. And so I first ask, well, what's the first possible edge? And then from there I say, what's the second possible edge? And possible edge to take. And you follow the questions all the way down, and at the leaf you get one of the solutions. And so then we can classify all these solutions based on what the answer is for the question we asked the bird. Right? We asked the bird what edge to take first. These are all the guys who take the first edge. These are all the ones who take the second edge. Right? And then for each of these classifications, we get our friend to help us find the best from each of these classes. Right? And then we take the best of the best. Does that kind of make sense? All right, so here's the basic code. And as I said, the code that I want to see on the test is going to look like this. Right? More or less. I think we have little underlines. Let's see if we have underlines. All right, so the first step is when you're thinking about coming up with code is to be clear about what the subinstance is. Right? So here's subinstances, a graph, a geometry-directed graph layer, nodes S and T. You want to be clear about what the solutions are, right? All right, so not only want to be clear about what the subinstances are, you want to be clear about what the solutions are, right? A solution is a path from S to T. You want to be clear about the cost of a solution, right? The cost is the sum of the edges along, and then, then skip the base case for a minute, and come down here and say, all right, now I have I'm trying to find the best path from S to T, and I'm going to ask the bird a question. So here we say, that what's the bird friend algorithm? The bird friend algorithm is the bird tells us what edge to take first, and the optimal path from S to T. And she answers, take the edge from S to VK. Right? And then we ask the friend for an optimal path from VK to T. And he solves this recursively, giving us back his solution. Right? This is the optimal solution to the sub-problem. And to the to the shorter path, we add on the edge that the bird gave us, and we go from there. And so now, and then we take the best of the best. So what do we have to do first in the code is you have to try all possible bird answers. So what's the question to the bird? We ask for the best edge leaving S. We ask which edge to take from S. And the bird answers go from S to VK. So here this is a loop over all the possible edges leaving S. Right? So in the code, I want to see, when you're writing this, I want to be clear. I want you to really specify clearly what answer does the bird give, right? You ask the best edge, and she answers go from S to VK. And another thing I always do is I always index her answers with K. If we just do that consistently, then we know, hey, K, that's probably her answer, right? All right, so it's good as a comment to put in here the bird algorithm, the bird friend algorithm. But quite honestly, on a test, I often say, all right, here's the problem. Give me the bird friend algorithm, and now give me the code. So you don't have to write this here because you've already wrote it in part A. All right. So what is the algorithm? Right? I said this already. What do you ask the bird? You ask for the first edge. What does she give you? She gives you an edge. You get help from a friend. What do you ask from the friend? You ask for the best path from VK to T. All right. So now look down here in the code. Somewhere you have to ask the friend. Right? In the code you have to ask the friend. And how do you ask the friend? Is we're given an input. Level graph from S to T, we recurse. Level graph, but we're going from we're asking the friend for the best path from VK to T, right? So that's where we're recursing, right? And our friend magically gives us the optimal solution. I call it optimal subsolution, not because it's a subsolution, but because it's the optimal solution to the subinstance, right? And he gives us the cost of that optimal solution, right? That's what we trust our friend to do for us. Then what do? Well, we take the solution, the path he gave us, and we add on the bird's edge, the bird's advice. So this is a path from VK to T. So together we get a path that goes from S to VK to T, right? You see that there? So now, I'm going to, optimal solution sub K, that's what I've produced here, right? I've produced optimal solution sub K. And what is that? You can use that, this notation, all of you can use this notation, and you should all know what it means. This is going to be the best solution to my problem, right? It's going to be a path from S to T, and it's going to be the best one of those consistent with the kth bird answer. Right? That's why it's indexed by K. And we also compute the cost of this solution. How do we do it? It's the cost of our friend's path plus the cost of our edge. Right? And then, once we do all bird answers, right? Then we have, for every bird answer K, we have, as I said, the best answer of those consistent with this bird answer. Right? And so then, we figure out, well, which of the Ks, which of the bird answers minimizes this cost, right? Which of these paths is the best? And our solution will be the one that's the best. And our cost will be the cost of that guy, and then we return that answer. People kind of follow that?
So, do you want to see this code? You said
Yes. I want to see that on the test. Actually, it's not. It's kind of a lie to you, because this is recursive backtracking, and the code I'm actually going to want to see is dynamic programming, and we're not there yet.
So what are we supposed to do with this? Actually, we're supposed to know it,
yeah.
You want to see parts of it.
Yeah, I want to see it. I want to see the code's going to look like this, but it's going to be for a completely different problem, right? So another thing, as I said before, is if I ask you for dynamic programming for this sum problem that you've never seen before, don't give me the recursive backtracking algorithm for SD connectivity, because, you know, they don't. Anyway, just, you know, try to, do you have any questions about this code now? Because we're going to be doing lots of examples too. All right? Now, of course, this is the general case. Like any recursion, you need a base case. And what's the base case is when the problem is so small that you can solve it on your own. And in this case, if you want the best path from T to T, right? What's the best path from T to T? Well, it's the NP path of cost 0. Everybody buy this algorithm? Yeah, and what's the NP, it's NP path of cost 0. And we make sure that for every input, we return the optimal.
Is it, for this one, everyone eventually got to T, can you have them where, like, say, V might also just stop? You can't get to T from there?
Yeah, for sure. For sure, and what would happen in the code is that you would increment over all edges leaving this S, and there would be no edges leaving S, so you would, so you wouldn't have anything, and here you'd be doing the best of the best, but there were none, so you would have to say, oh well, then put infinity here or something, right? So it goes back to what's the minimum of the empty set? Well, I guess it's infinity. All right. So we needed this optimal substructure, and this slide's kind of confusing. So don't worry about it too much. But in order to be able to do this recursively, you need a sort of a recursive substructure. And what does that mean here is, you know, if I want to get from my house to York, right, and I've decided that I go to St. George Station, and I know the optimal solution, optimal path from St. George to York, right? Then given that I go to St. George, then that's what I should be doing, right? That makes sense? I mean, it's not true for every problem, but for this problem, it makes sense that there's sub-instances in there whose solutions are significant to our solution, right? And what's the proof of that statement as well? If there was a shorter path, then, you know, I would take it, right? So that was just a little, and so the task of finding the sub-problem is useful to us. So an optimal substructure means that every optimal solution to the problem contains an optimal solution to the subproblem. All right? It doesn't mean that if you have I actually got this slide for, you know, usually James steals them from me. I stole this one from James. I think this is the only slide I stole from James, so I'm not really completely up on it. But you know, he has this example here where if you want to make 7 cents, you know, this is the optimal, right? The optimal, right? Oh, I guess this is the optimal for 7 cents is this, and the optimal for 6 cents is this. But then you think the optimal for 13 cents should be the union of the two, but it's not. I don't know. All right, so here's an example which I think is kind of interesting. Actually, I stole these slides from him, this whole sort of section. Right, so if we're doing longest simple path, right, instead of shortest path. Shortest path is easy. Longest path is actually a really hard problem. Longest simple path is a hard problem. So if you're looking for the longest path from A to D, what's the longest path from A to D that's simple? You know, you kind of do this, right? Simple means you don't spiral around, right? So there's really only 2 paths. You can go this way, or you can go this way, and this one's longer, right? You can't go like this because then it's not simple anymore, right? So he's saying here that the longest path from A to D is A, B, C, D, right? And the longest path from A to B, however, is this. Right?
Oh.
You see that? So that kind of messed up what we were just talking about. And that's why longest path is harder than shortest path.
Would you ever want to do that though? In reality?
Would you ever want to solve longest path?
Yeah, like find the longest path or something.
You know,
Like, what
I think it's NP-complete to find the longest path. In which case, if you could solve it, you could solve all NP-complete problems and life would be good. So, are there applications where longest path is useful? Surely you can make it. You know, you're trying to get from here to home to do your homework, and you want to make, you know. Right. This is just kind of what we're saying already. Oh, there you go. And it's, I think I added that one. It's implicitly. All right, so now somebody over there said that this is brute force. All right, so the truth is that the algorithm that we just talked about is brute force. Why? Because we try all edges out of S. Those friends try every edge out of theirs. They try every edge. They try every edge. And so really it boils down to is we're trying every path. Right? And this is brute force. It's exponential time. Right? And so one might ask, why did we do all this work to when we could have just as easily done enumerated through all the paths. Right? So I have right, so this is what we just said, exponential number of paths. Why did we do all this work? I have a couple of arguments for why this is useful. The first argument is, okay, so you want to do brute force. You know, you're patient and you want to do brute force. I dare you to write an algorithm that iterates over all paths from S to T. Right? How do you even do that? Right? How do you write a path that says, okay, give me the next path from S to T? Right? And make sure that you hit each one and hit each one only once. If you wanted to do that, this is the way to do it. Right? You first iterate all the ones that go through the first edge, and then, right? So it's a good way of thinking about the set of all paths anyway. And also, the other advantage is this has given us this structure for talking about doing this. And once you have a structure and think about it, you can find ways of speeding it up.
Could you do something, I don't know, because you're coming down from like 1 to the path. Could you somehow just figure out what the shortest one was for that one and keep doing it, and if you ever get like a total, somehow just keep jumping around between the ones that have the total, so you might not go through all of them or something?
Yeah. Yeah, there are a lot of creative things you can be trying. Right, so we're going to be talking, I mean, one option is to try to prune off entire branches of this tree. Right, you might just, maybe this is kind of what you're saying. For example, if this edge cost 5 billion in itself, you'd already found a path of length 10. Right, it's like, you know, skip it. Right, so that's one good to speed it up. Right? Maybe you can discover that all of these paths, for some reason, aren't valid or just cost too much. Right? Now, here's another thing. Suppose this was an optimal solution. This one right here. Right? Would it be a disaster if we pruned off this branch? If there was another optimal solution here. Right? Remember what we were doing with the greedy algorithm? It was okay to burn some of your bridges, you just don't want to burn all of them. Right? So we prune things so that we know that there exists an optimal solution consistent with the things that are remaining. Right? So this is what it's saying down here. It's okay to prune that as long as you know there's another optimal solution. And in fact, what the greedy algorithm is exactly that. It's sitting here and it says that this is the best, best choice, greedy choice, and it prunes the rest of them. And the reason it can prune them is because it knows that if there was an optimal solution there exists another optimal solution consistent with it. And the way you prove that is you take this optimal solution here and you massage it like we did to the fairy godmother, and you change it into one that's over here. Right? And so that's what the greedy algorithm is. All right, but we're not good. This is a good techniques, and you can do whole PhDs, and you devote your whole life to doing this faster. And that's not what we're going to do right now.
When you're doing these, if you have something where it comes down like this and then it comes down to here, would you end up checking this node twice? Once for this path and then once for this path?
Yes. Yes. Good. That was very good. That's what we're going to do right now. All right? So this is called memoization. Now, I'm not a good speller, as you may have noticed at some point. And for years I looked at that word and thought, what the hell is that word? And I thought it was some sort of misspelling of memorizing, right? But then somebody, I think it was some student in some class, pointed out that no, it comes from memo. Memo, to take a note, right? To take notes. So that's what we're doing. We're taking notes. All right, so what we're going to do is if we run this recursive backtracking algorithm, that's what that algorithm is called, is recursive backtracking. Why? It's because you try something, you recurse, and then when it comes back, you backtrack and you try something else, right? Recursive backtracking. Right. So now you have these sub instances, and what they're going to do instead of they solve their problem, instead of giving you the answer and then committing suicide, is they're going to stick around and they're going to remember their answers. So if you ever need to solve the same problem again, you can reuse it. All right? Which effectively it prunes off that branch because you don't have to redo it. All right, so let's try this example, and it's exactly what he was saying. Right? Here's a question: what is the best path from V7 to T? Right? And we can ask, do I have any friends who are going to have to solve this problem? And how many of them are going to have to solve it? Well, if this is me, I need the best path from here to here. I'm going to ask this guy, right? Who's going to ask this guy? Who's going to ask this guy? Right? So that problem needs to be solved. Right? But let's start again. Right? This is me. I ask him, who asked him, who asked him. Right? So here this problem is getting solved again. It's getting solved twice. And in this case it's pretty short, so it's not a big deal. But it gets getting solved over and over again. And so how many times does this guy have to get solved?
1, 2,
3.
Once for every path from S to V7. Right? Every time there's a path from S to V7, this guy gets resolved. And there's an exponential number of paths from S to V7, and so that's problematic. Right? Everybody see that? So, big waste of time. And we're going to save our time by doing it only once. All right? Depth first search. What? Did we do depth first search already? I think this is just a reminder that you save stuff so that you can reuse it. But let's not worry about it right now. All right. All right, so we have, right, the way we've done it so far is there are all these friends who are solving the same instance. Right? And what we're going to do is we're going to get rid of all of them, and we're going to allocate one friend to this node, to this subproblem. Right? There's one guy who's going to be trying to get the best path from V7 to T. And that's his job. All right? All right, so this is what it says. It says, my job is the best. My job is to learn the optimal solution for the subproblem and to remember it. Right? So, for example, when this guy here, right, his job is to find the best path from V4 to T. Right? And how does he do it? Is he asks this guy here, which we can call Mr. V7 because he's trying to find the best path from V7 to T. We ask him, and he then says, hey, great, I'll tell you. He goes off and he finds the answer and he tells him. Right? But now, when this guy is trying to find his best path, he asks him again. Right? And so what does this guy do now? He already knows the answer. Right? Does that make sense? Everybody good with that? And then similarly, when he does it, he knows the answer as well. Now, another problem is that we're impatient. We don't like to wait. Right? And we also, all right, thanks. We also don't like a lot of overhead, keeping track of who's waiting and who's going and stuff. Right? So, by waiting, we mean this guy wants to know his answer, so he asks him, and he doesn't know the answer, so he goes off and solves it. Right? That's waiting. So, right? He hates to wait. So, and the recursive overhead to avoid waiting. He says, why don't you go first? Right? So now what we're going to do is this guy, he's going to go earlier. He knows that eventually somebody's going to ask him for the best path from V to 7, so he goes off and figures it out. And he stores it. right? So he's already gone, so that when later people need it, he's there and he's ready. So now we need to know what are all the subinstances that we need to solve, right? So what you think about it, and in what order do we want to solve them? All right, so this instance is the best path from S to T. We need to solve that one. Why? Because that's the main problem we've been given, right? So imagine running the recursive backtracking algorithm on this, right? I have my friends, they have their friends, right? Right? My instance is this, my friend's instance is this, his friend's instance is this. You think about all the sub friends, and you want to determine the complete set of subinstances that is ever going to arise, right? And we're going to guess the set. You know, you think about it and you guess. All right? So, for example, V7 to T, is that going to happen? Yeah, we did that one already, right? What about the best path from V21 to T? Is that ever going to come up? No. No, V21's on the, you know, where did that come from? No. Right? What about the best path from V3 to V7? Is this going to ever happen? We have one vote for no. How many people vote for no? How many people vote for yes? How many people vote for I have no idea? All right. A no person, tell me why.
Because everybody wants to get to T, nobody wants to get to V7.
Everybody wants to get to T. Right? Exactly. No, why? Because all paths considered indent T. It's kind of proof by, right? I want indent T, he wants indent T, he wants indent T, he wants indent T. Nobody wants to go anywhere else. T is a great place. Right? So that's proof by picture. Everybody wants to go to T. All right, so what about the set for all best paths, you know, from every node to T? Right? That's, we're guessing, is our set of subinstances. Does that sound right? Yeah, we need all of those. And to each of these, we assign a subinstance. Right? We assign a friend. Right? This guy here, Mr. V3, his job is to get from V3 to T. All right? How many minutes have we got? Nothing. 2 minutes. All right, excellent. So, here are some requirements. When you're trying, one of the hard parts about coming up with the dynamic programming algorithm is coming up with a set of subinstances. All right? So, the way you do it is you first kind of trace it out and you guess, and you write down what your guess is. Right? For every node, the best path from that node to T. And then you check to make sure that you have the following properties. All right? The first property is that your set better includes your original instance. Right? The second guess is that it needs to be closed under what I call the friend operation. What does that, you know what does it mean for the integers to be closed under addition? Right? You take two integers, you add them together, you get an integer. You take two even numbers, you add them together, you get an even number. Right? You take two primes, you add them together. No, you don't get a prime. Right? Right? So for every two guys, you add them together. Right? So this says for every instance that we're going to consider, you need all his friends that better be in there. All right? So let me tell you another story, because you know I like stories. Let's talk about getting married. Right? One of the big problems when getting married is who to invite. And here's some rules. When you get married, you better invite the bride and groom. Right? And if you invite somebody, you better invite their friends. Right? So those are two rules. And the problem, what's the problem with that?
Everyone has friends.
Everybody. You know, before you know it, the entire world is coming, right? So that's, in fact, and when I gave this, talked about marriage in the book, the publisher said, no, that's a dumb example because everybody in the world is going to come to your marriage. And that's exactly the problem with dynamic, that when you try to do dynamic programming, is if the entire world's coming to your marriage, then you're going to have a, you know, it's going to be expensive. Right? Right, so the last thing we need about is that everybody's sort of needed. We need this guy because, you know, you don't want a lot of extra subinstances in there. All right, that's all we got for today. We'll continue with this on Wednesday, and then as you know, everybody know what's happening. Oh, then we have Friday, and then we have Monday again.
Is that the way the calendar works?
That's the way the calendar works. And you know what's happening.